Alright, now let us tackle KD trees. KD stands for k-dimensional. And I have a data set here, features x1, x2. Yeah. And what we're going to try to do is decide on the label of the red cross here, x. Yeah. One way of doing it, we could use k nearest neighbors. Well, what's the problem with k nearest neighbors? Well, first of all, if you have a lot of data, it's going to consume a lot of memory in your machine. And also you need to calculate all these distances if you have a lot of data, and this will slow the algorithm down. So is there a better way to do it? And the answer is yes. So basically what we're going to do, we're going to split the data set, and we're going to split it each time along the median of the axis with the highest variance. So let's take a look here. Yeah. So I decided to split here because this is the largest variance along the axis of x1. Yeah. And then we can further split. Then the largest variance will be along this axis, and we can split again. Yeah. Now, the claim that we're going to make now is that the nearest neighbor to the red cross and the distance of the nearest neighbor to the red cross is always smaller than the distance of any point A on the left side of the split. Yeah? So that means that while splitting, you actually eliminate all the data points on the left of split number 1. Yeah? So again, we're going to prove that the distance from the red cross to the point A here will always be bigger than the distance from the red cross to its nearest neighbor. And in our case, this one here is the nearest neighbor. So it's easy to prove. We will use Pythagoras. And by the way, this one we call split number 2. So Pythagoras says, so we have here the point A, the red cross, and we call this distance D, this distance C. The distance from the red cross perpendicular to the split is called A. Yeah? And the distance between the red cross and its nearest neighbor we will call NN. Okay? Now, we work in this small triangle here, and we know that C squared is A squared plus B squared. That is the famous Pythagoras theorem. So that means that C equals A squared plus B squared, and we take the root. Yeah? Now, if we want to know what C plus D is, C plus D equals square root of A squared plus B squared plus D. What we're going to do now is we're going to eliminate the B square. Now we're going to eliminate the B square. We made this one smaller, so this one is larger. Yeah? And the square root of A squared is A. So that means that C plus D is larger or equal than A plus D. Yeah? And A is larger or equal than the distance between the red cross and its nearest neighbor. The range given by the orange circle here. You see the radius of the circle is always smaller than A. If it would not be, then the nearest neighbor would be on this side. Yeah? And we said the nearest neighbor is on this side. Yeah? So here, this one here means that C plus D is larger or equal than A. And if I combine these two, then we see that C plus D is larger or equal than the nearest neighbor. And that's exactly what we wanted to prove. Alright, let us now take a look how we can make the link with a tree. Because this is the subject of this lesson. We have another data set here. Yeah, it's a binary data set. We have circles and crosses. And we have a point here with coordinates 10, 3, where we are interested in finding out the label of this point, of this test point. And of course we're going to split, and now we're going to make the link with a tree. So we start with the first split along the median of the axis with the highest variance. That's this axis. The median is about 5.5. So let's call this split number 1. Yeah? And we branch out to 2 leaves here, yeah? Where x is smaller, x1 is smaller than 5.5, and here x1 is larger than 5.5. Yeah, we're not interested in this piece because our test point is there. So here we're gonna do another split, but we're gonna do a split now across x2 because now this is the largest variance. Yeah? So we do another split. Yeah? Split number 2. Yeah? And split number 2, we have again 2 options. That x2 is larger than 4. x2 is larger than 4, and we're not interested because it's this area and our point is in this area. Or x2 is smaller than 4. And then you're basically playing this rectangular here. And what do we have? We have still three items with a circle and 5 items with a cross. Yeah? You can see that this leaf is not a pure leaf. The circles we call the leaves of the tree. It's not a pure leaf. Your chance of picking the wrong class is still relatively high. Yeah? You could actually split further until you have only 1 point per leaf. But you got to be careful that you do not overfit. Here again we need to trade off. And so we need a metric that defines the impurity of the leaf. And there's 2 metrics we're going to look at. One is the Gini impurity. The other one is entropy. It gives you the quality of your split. What's your chance of still picking the wrong class? In this case here, the chance that your test point is a cross, is 5 out of 8. 5 out of 8. And its circle is 3 out of 8. Yeah? So some formalities now. Let's call S the set of labels. Yeah? In our case, S equals the circle and the cross. We only have 2 labels. Sk are all the points with label K. Yeah? We can decide in what rectangular we will measure. But, for example, S cross equals all the points where the label is a cross. Yeah? So that's as simple as that. And of course, if we sum up all the SKs, we're gonna have all the points of the data set. Yeah? So it's quite obvious that S is the union of all the SKs. Now the probability of the class K, your probability of picking the class K, is gonna depend on how many of your points are classified as K versus the total amount of points in your data set. That's quite obvious. Yeah? So the Gini impurity coefficient, it's Gini impurity, has nothing to do with Gini coefficient. The Gini impurity is defined as the sum over all classes, the chance you pick class K times the chance that you pick the other class. Yeah? In our case, we only have 2 classes. Yeah? So it's relatively easy to calculate. So let's do this. So in our case, is the chance of a cross 5 of 8 times the chance of a non-cross is 3 out of 8. And then we're gonna add the same. Yeah? Here you have 3 out of 8 times 5 over 8. So we're gonna do that times 2. 15 times 2 is 30, divided by 64. You see here that your Gini impurity is quite high. Yeah? You're going to be roughly in the middle here. And this is not what we want. We want to be as pure as possible without overfitting. Yeah? So we want to be as close to 0 and 1 as possible without overfitting.